Hi everyone, welcome back to week 6 of statistics. This week we're going to look at probability tied into tree diagrams, or using tree diagrams as a way to work through problems that deal with probability. So one big thing that tree diagrams build off of before we get into this is when you're working with a tree diagram, we bring the idea of complementary events up a big time a lot. So if you recall, visually when we're talking about the complement of an event, if we have some set here, and this is A, everything that occurs, the probability of A would be everything inside of it. The probability of A complement is everything outside of it. So if you look at this, if I've shaded A and A complement, I've shaded everything. So all outcomes are considered when we combine A with A complement. If we do that more abstract or using symbolic notation, if I take the probability of some event A happening and add it to the probability of that event not happening, or the complement of it, this always equals 1. Because if I say something is happening, or is what we use addition to represent, that event does not happen. So if I have the event happens or it does not happen, that probability always has to equal 1. So we're going to use this bit of information quite a bit in tree diagrams. So let's get into this and see a tree diagram problem. So here it is. The probability that it is raining today is 0.6. If this is the case, the probability Jack walks to work is 0.3. If it is not raining out, the probability Jack walks to work is 0.75. So we want to represent this information in a tree diagram. So the way we do this is we're going to build a diagram that shows all the outcomes that can happen. So the first thing I'm going to consider is Jack walking to work. So here I'll head this as walking, and then I'll head the other part as if it's raining or not. Because him walking to work, let's flip that actually. It raining impacts him walking to work or not. There we go. So raining outside decides if he walks to work. So when we build a tree diagram here, two things can happen with rain. It can either be raining or it is not raining outside. So one of those two events will occur, and this is where the complement is going to get into it. So now, if it's raining or not raining, that determines if Jack walks to work or if Jack does not walk to work. And similarly, with not raining, he walks to work or he does not walk to work. So what we've just done here is we've shown the sample space, or all outcomes that can happen. Now we can assign probabilities to these. I like to assign the probability of the event happening to the branch of this diagram rather than at the end result. So as I follow it along to find outcomes, I know exactly what I'm multiplying by. So up above, it said the probability that it's raining today is 0.6. So 0.6 is the probability it is raining today. So what that tells us is we can find the probability of it not raining. If there's a 60% chance, or 0.6 is the probability of it raining, 0.4 is the probability of it not raining. In tree diagrams, when we add vertically, every time we add vertically for that outcome, it should equal 1. So now, consider it raining or not raining. Jack either walks to work. Well, the probability of it raining, we're in this branch now, this branch of W, probability Jack walks to work is 0.3. So when we're looking at this vertically, we're only looking at everything above this dotted line, because this is a different outcome, different set of outcomes there. So it raining and him not walking to work would be 0.7. So these add to be 1. Now, if it is not raining out, the probability Jack walks to work is 0.75. So not raining and walking, 0.75 is what that probability is. And finally, that would mean that there's a 0.25 probability, or 0.25 is the probability of him not walking. These add to be 1 as well. So there's our tree diagram with probabilities assigned to each outcome. So let's try a problem now. So based on what we just created, we want to find the probability it is raining and Jack does not walk to work. So when we go through this, we just follow the tree diagram to the outcome we'd like. So I'm just going to highlight this. So we want to find the probability it is raining. So probability of it raining, there we have it, and Jack does not walk to work. So does not walk to work. So when I say and in these, it's important to note that and tells us to multiply here. So if I want the probability, that's R. If I want the probability, I want to get this font a little different. The probability of it raining and Jack not walking to work, I multiply, because the probability of it raining and Jack not walking to work. 0.6 times 0.7, which is 0.42. So there we have it. 0.42 is the probability that it's raining and Jack does not walk to work, out of all the outcomes that can happen. Second one, what's the probability that Jack walks to work? Well, now we want to consider all of the ways we can hit this outcome. And there's two ways we can do it. We can have the probability that it is raining out and Jack walks to work, or we can have, or when we say or we add, we can have the probability that it is not raining out and Jack walks to work. So both of these end in the walking to work. So both of them end in walking to work. So now we need to go through and multiply these. So 0.6 and 0.3 is it raining and Jack walks. So 0.6 times 0.3. Or we can have the probability that it's not raining, which would be 0.4, not raining and walks to work, times 0.75. So 0.4 times 0.75. I probably should have put parentheses or something around these to make it a little clearer. So 0.6 times 0.3 is 0.18. That's the probability that it's raining and he walks to work. 0.4 times 0.75 is 0.3. So we add 0.3 to this and we get 0.48 for that probability. So this is one way we can work with tree diagrams. And these are based on two events that are independent. They don't really tie into each other that much. So now onto the second sort of problem. And this should look very familiar because this is the exact same problem that we worked through last week. So we have a bag of marbles, contains 3 red, 5 blue, 7 yellow. 15 total marbles. 1 marble is drawn, returned to the bag, and a second marble is drawn. What's the probability that at least one of them is red? So if the solution I posted earlier didn't make sense, hopefully this can clarify things and give you a little better understanding. Another approach to it, this is more visual. So we only care about it being red or it not being red. So in this case, I'm not going to go through and put 3 outcomes because all I care about is when I draw the first marble, it being red or not red. So those are the 2 outcomes. So we have red and then we have it's not red. And then when I draw the second marble, that's all I care about. Again, I'm making this a little easier than doing red, green, yellow because that's going to get messy. I have 3 outcomes and it's going to build into this giant tree diagram. So second outcome, again, I only care about it being red or not red. And then similar with the not red branch, it's either red or not red when I draw it for the second time. So now let's assign these probabilities. This time they're going to be as fractions. And that's okay. That decimal is the same thing as a fraction. We just represented it in a different form. So the first marble being red, the probability is 3 of the 15. So that means the complement of that would be not red. So that would be 12 of the 15 are not red. And because we replaced the marble, it's returned to the bag, we have the exact same branch or probabilities for red and not red. So 3/15 and 12/15 and 3/15 and 12/15. I think you can see where this is headed when we start not replacing or working without replacement. These denominators would change. So what we want is the probability that at least one of them is red. So if we follow this along, we can find every single branch that has at least one red. So we'd have red and red. So that's red, red. Or we'd have red first and not red. Or we'd have not red first and red second. So all of those outcomes are what we're interested in. There's another way you can do this actually. If you notice there's only one of them that isn't highlighted, we could find the complement of that. But let's just go through it the way that we initially worked it. So starting out, if we go with red first, red second, that would be the probability of red, red. So the probability of red, red, which is 3/15 times 3/15. Or, add when we say or, probability of red first and then not red. Red first and then not red. So that's 3/15 times 12/15. Or we would have the probability of not red as our first marble, and then red as our second. So that would be 12/15 times 3/15. And just like we did in the last problem, 15 and 15 is 225. And then we end up with 9, 36, and 36. So 36, 36 makes 72. 9 is 81 2/25, or 9/25. So there we have it all the way through. So using this other approach to work through a similar problem. So this does it for the types without replacement. We'll look for the next video, work through the practice problems first, and then the final video will be covering without replacement. I hope this video helped. Let me know what questions you have.